Ever wondered how your computer's brain actually understands and runs code? Today on Knowledge Hub, we're diving deep into how a CPU, the central processing unit, executes instructions and brings your software to life. At its core, a CPU is an incredibly fast and complex electronic circuit that follows a simple but powerful loop called the Fetch-Decode-Execute cycle. Everything your computer does, from running a video game to calculating a spreadsheet, is made up of millions of these cycles happening every second, or even every nanosecond. Let's start with how it fetches instructions. Every program you write, whether it's Python, C++, or Java, eventually gets translated by a compiler into machine code, binary instructions of ones and zeros that the CPU can understand directly. These instructions are stored sequentially in the main memory, RAM. The CPU has a tiny internal pointer called the program counter, which keeps track of which instruction to execute next. During the fetch stage, the CPU sends this address to the memory controller, retrieves the instruction from RAM, and stores it temporarily inside a special register called the instruction register. After fetching, the program counter is automatically incremented so the CPU knows where to look for the next instruction. Next is the decode phase. This is where the magic of understanding happens. Inside the CPU, a specialized circuit called the instruction decoder reads the binary code and figures out exactly what operation is being requested. For example, a code like 100000010 might mean add these two registers, while 11000011 could mean store data in memory. The decoder translates these bit patterns into control signals, which are electronic commands that tell other parts of the CPU, such as the Arithmetic Logic Unit, ALU, register file, or data buses, what to do next. The control unit, which manages this process, acts like the CPU's conductor, making sure each component works in perfect coordination. Then comes the execute phase, the part where real computation happens. The CPU's registers, which are small, lightning-fast storage units, hold the actual data to be worked on. For arithmetic operations like addition or subtraction, the ALU takes two values from the registers, performs the calculation using digital logic gates like AND or NOT XOR, and stores the result back in another register. For more complex operations like floating-point math or trigonometric calculations, a separate unit called the floating point unit, FPU, comes into play, designed specifically for precision numerical processing. But what makes modern CPUs truly powerful is that they don't wait for one instruction to finish before starting the next. They use a concept called pipelining, which breaks down instruction execution into several overlapping stages: fetch, decode, execute, memory access, and write back. This means while one instruction is being executed, another is being decoded, and a third is already being fetched. It's like an assembly line. Each stage handles a different instruction simultaneously, dramatically increasing throughput. Taking it a step further, CPUs often have multiple pipelines. This is known as superscalar architecture. It allows several instructions to be fetched and executed in parallel using multiple ALUs and FPUs. To make this efficient, the CPU uses branch prediction to guess the direction of conditional statements before they're resolved, reducing stalls and keeping the pipeline full. If it guesses wrong, it simply flushes the incorrect path and continues. Another advanced technique is out-of-order execution, where the CPU doesn't necessarily execute instructions in the exact order they appear in the program. Instead, it dynamically reorders them based on available resources, ensuring no time is wasted waiting for slow operations like memory fetches. The results are then reordered back into their original sequence before being written back, keeping the illusion of sequential execution while massively improving performance. All of this is synchronized by the clock, the CPU's internal heartbeat, which ticks billions of times per second. Each tick or clock cycle represents an opportunity for the CPU to advance an instruction through one stage of the pipeline. A 5 GHz processor means 5 billion of these ticks every second, and because of pipelining and parallelism, multiple instructions are often being processed at the same time. To make things even faster, modern CPUs have multiple cache levels, L1, L2, and L3, which store frequently accessed data much closer to the processor than RAM. Accessing data from cache can take just a few cycles, while fetching from RAM might take hundreds. The CPU's cache controller predicts which data and instructions are likely to be needed next and preloads them to minimize waiting time. And finally, when your system has multiple cores, say 8 or 16, each core is essentially its own CPU capable of running its own threads of code. Combined with simultaneous multithreading, like Intel's hyperthreading, each core can handle multiple instruction streams, further improving parallel performance. So the next time you run a program, remember that under the hood, billions of microscopic transistors are working in perfect harmony, fetching, decoding, and executing at blinding speeds, turning simple binary code into the smooth digital experiences we rely on every day. If you enjoyed this deep dive into how CPUs actually work, make sure to hit that subscribe button, because here on Knowledge Hub, we make complex tech crystal clear. And as always, stay curious.